Ann-Cathrin Engwall on kavandanud ja arendanud ja tegelenud vaktsiinide tootmisega kliiniliste uuringute jaoks. Et see on inimene, kes on konkreetselt vaktsiinide tootmistega tegelenud. Ja doktor Engwall on olnud Rootsi riikliku ravimarenduse võrgustiku liige. Praegu on ta Akemkon AB tegevjuht ja pakub oma teadmisi konsultandina. Et nagu me teame, meie kõikide karjäärid käivad lainetena. Kord oleme me ise õpilased, siis me õpetame teisi. Kord me töötame tippkohtadel ja siis me konsulteerime neid tippkohtadel olevaid inimesi. Mycket välkommen, Ann-Cathrin Engwall.
Tack.
Och varsågod.
Tack så mycket. Oj, vad högt jag hör min röst, men det är bra. I will talk about mass vaccination, especially against respiratory virus. And because they are very fast mutating and they are spreading fast, and that could actually be counterproductive to mass vaccinate in such a situation. So I want to address some of the issues or the arguments that is put forward by officials that actually is not true or are not totally true. Anyway, I have to go through some backgrounds first, so you will understand what I'm talking about. There are two main types of immunity. One is against intracellular threats. The other is against extracellular threats. For the intracellular threats, it can be cells that are dangerous for the rest of the body. That could be cancer cells, or it could be virus-infected cells. Virus, as you probably know, cannot be independent. They need the host cell system to replicate, and therefore it's more like a parasite, I would suggest. And your infected cells is actually producing a lot of viruses. So the cell has to get away, you have to get rid of the cells producing virus. So in that system you have T killer cells that will kill all virus-infected cells. Not all, but most of them. Then you have extracellular threats, and that is everything outside the cell. For example, like bacteria. And in this case you have eater cells that will eat everything or take up everything outside the cell. They're more like a cleaning function. And these cells will break down like a bacteria or a virus particle into pieces and present it to the immune system. And that's when you get antibody production. So remember, intracellular threat, T killer cells. Extracellular threat, outside the cell, you have antibodies protecting you. That's the main thing. I also have to show the general structure of a virus. This is true both for influenza virus and for coronavirus. And you have the genome here, and the genome can be either DNA or it could be RNA. And if you have an RNA genome, like you have in the coronavirus and you have in the influenza virus, it mutates very, very fast. And that depends on the enzyme that have to take part in the replication process are very ineffective, so that they make a lot of mistakes that is not corrected. So in principle, every person who is infected has several mutants, but only a few of them are successful. Okay? The genome is then surrounded by a nucleocapsid, and that is a protection for the genome. And then it is a fat membrane. This is not all viruses have that, but both coronavirus and influenza virus have a fat membrane. And this fat membrane around the cell particle is actually stolen from the host cells, the cells that are infected. So the virus particle takes part of the cell membrane from the cells they are infecting with them when they are produced. And everything inside this envelope or the lipid layer is actually, I call it the inner proteins or the inner Ja, kan jag också peka på den. Bra. It's the inner proteins, and that is important to remember in my arguments later on. Here, then you have the surface proteins, and the surface proteins is the spike protein, or for influenza is the H or N protein, and this is actually the function of docking to your host cell, binding to the host cell, and also get introduced, also be taken into the host cell. It's also the only part of the virus that antibody can recognize and bind and neutralize is actually from the outside. And that means that the inner side of the virus, like from the nucleocapsid and other proteins, will not be eliminated by antibodies. It's only the surface protein. And it's also the place where most mutations occur, both because they try to avoid the immunity, antibody immunity, but also it is adapting to become more effective in its infection process, and that gives a competition advantage. So that is the most variable region in the virus, is the surface proteins. And it's also here where you construct most of the vaccines that you use for this type of viruses, because this is the only part that can be recognized by antibodies or neutralized by antibodies. I will just show you how an infection looks like. The red represent, the red here represent the virus load. That means how many virus do you have in your body. The blue, this one, is actually representing the number of T killer cells, actually the cells that are the cell-mediated immunity. The green here is antibodies. So you see that first, in virus infection, what's happened first is actually killing of virus factories. The second is cleaning of extra material and virus particles outside of the cell. So the antibody response is secondary in virus infections. Important, but secondary. It's also important that you have antibodies long-lasting, that are T killer cells, and that is important because it stops you from getting infected with exact same virus. And then, if you get reinfected, it looks like this. First, when the T killer cells start to increase, then the virus load goes down quite fast. So viruses are eliminated as within half the time as the first time. And it also depends a little bit how much virus you get from the start. But what you can see here is the importance of the killer cells for long-term protection. It's increased 8 times in the reinfection phase, while antibodies doesn't have that higher stimulation, or what to say. Yeah, here's a nice example of a study done by a Nobel Prize winner called Doherty. He got the Nobel Prize in 1996, the same year as I got my PhD. I actually had to move my my presentation for my thesis and defend how I defend it, because the committee had to go to meet this Nobel Prize winner. Anyway, he got the Nobel Prize because he showed how the cell-mediated defense works. And here's a very nice experiment too. He infected one group with mice with a flu virus, 2 different flu viruses that have the virus inside are quite conserved compared to the surface protein, but the surface proteins were different. Then they had one group that it wasn't pre-treated at all, and then these 2 groups, after recovering, were infected by a very pathogenic avian influenza virus. And you can see it has totally different surface proteins. what happens? First of all, the group that didn't get any treatment, only 10% of the mice survived. Sorry, doesn't matter. But in the other group that has been pre-immunized with in one way, different influenza virus, 2 different influenza virus, 90% of the mice survived. That's a quite big difference. And that is it's due to the cell-mediated defense, which is against these internal proteins, which is very, very important for the long-time protection against virus infection, especially when you have fast mutating viruses. Just to describe a little bit, this is vaccine. Normally you get antibodies here direct to the outside of the virus. That can stop an infection. But if the antibodies doesn't work fully, you will still have an infection, and these antibodies will have no use then. So if you get infected naturally, you will also have a T cell memory here that will be directed both to the surface proteins but also to all the inner proteins, because your cell that is infected will produce all the virus proteins and then will be presented on the surface of the infected cell. So they will be recognized by the immune systems. So even the inner virus proteins will be causing killing, which I think is very, very good to have. And this, of course, gives you less variation. The less variation it gives you much longer protection over time. You can get infected, but the consequence is you don't get so much virus, and the consequence is not so severe. So cellular immunity central for protection against viruses. Here's an example because I was involved already in 2009 in the swine flu mass vaccination as a critical. And I actually looked at the age distribution of people who were tested positive for this swine flu. And what you could see is a very unusual distribution. The most infected were the people between 10 to 30 years old, and the older people had very low. They didn't get infected and they didn't die. So it was actually very concerning death rates. It had very low death rates because the younger people often are stronger and they don't die from this type of infection. And then I made this. These people have been living during the time Asian flu and Hong Kong flu. And that's actually infections that they had as children or as young adults actually protected them so many years later. This is essential. Immunity is something that is consistent, but the virus changes. So an infection you had 50 years ago can protect you from another virus many years later if you have the T cells immune response against inner cell proteins, because they are something like 70% similar in influenza case, which is quite a lot. So the argument which is often put forward for promoting mass vaccination is stop virus from spreading. Have you heard that? You have to behave solidarically and vaccinate you to protect your older, more weak relatives. Yeah. Reduce the risk for severe symptoms and death. And reduce the costs for hospital care and sick leave. I think this is something that is very important for politicians. I think that's the main argument for them, as I will show you later. And also to improve public health. So, stop virus from spreading, I would say. As you know, if you had an influenza vaccine shot, it will only last for a year. Then you have to get another one. But if you have natural immunity, how many times a life do you really go through a real severe influenza? Not many, maybe 1, 2. Not many times, I would say. So that is the difference. And viruses mutate a lot. And depending on the immunity, herd immunity in the population, it's putting a pressure for the virus to escape the immune system, because it's the only way it could survive, to avoid the antibodies that will stop them from infect. So another other thing I saw quite early in the corona pandemic was that it doesn't matter if you get infected, whether you were vaccinated or not, you get the same virus load. And that actually determines how contagious you are. It's not, it's a difference. If you carry a lot of virus, you can spread a lot of virus. Then you are more contagious. If you have less amount of virus, you are less contagious. I will show example of this. This is how the coronavirus developed during a year. And all these dots here are different mutations that were been isolated during the first year. And you can see the evolution here. And this is thousands of mutations only during 1 year. And this is only samples that have been taken and sequenced. Probably many more variants were existing. So to tell, in the beginning I heard that, this virus is not mutating. And I was, no. Of course it's mutating. It's coronavirus. It's an RNA virus. So it will mutate. But not all mutants will be win the competition. So what type of variation will increase their competitive capabilities? Of course, if they can replicate more fast, if they can become more and more in a faster, of course they will take over from the old variant. Another thing is that they are more effective in getting into cells. And the third one is to escape from the immune system, mainly the antibody response. So those three will put pressure on the virus to change, because these changes will make the virus more effective, and then it will win over older variants. So when you get sort of herd immunity against one variant, others will take over because they will be more effective. So here is what happens when you do mass vaccination. First of all, you get a synchronization of the vaccine-induced immunity is against in this case, the spike protein from the beginning of 2020 or something like that. And everybody will get the same immunity. And this is not the normal case with normal infection. We all get infected by a number of different mutants. Also in our body, so we'll have a much broader antibody response also. So you will synchronize whole population. For me, this is very dangerous, especially since I know there will come new variants, and it will be a very high selective pressure to avoid this immunity. Actually, this will enrich vaccine-resistant variants, and I saw something in Israel quite early. The beta variant of the coronavirus, that is the South African variant, when they analyzed people, they saw that this variant was 8 times more common in vaccinated people than in unvaccinated people. So it's actually, the vaccinated people actually promoted and enriched vaccine-resistant strains. So that means that people who really need protection from vaccine, they lose their vaccine protection very, very fast. And that is why we need to take 1 and 2 and 3 and 4 and 5 shots with shorter time in between to keep but I don't know if it works, but that's how they think anyway. So actually it's like a cat and rat fight, because virus and your host immune cell system, or your host immune system will develop together. The other one will impact on the host immune cell, and the host immune cell immunity will have impact on the virus evolution. Okay, this is, I show you, this is showing that virus loads are the same if you are infected, whether you are vaccinated or not. This was from a report from CDC in July 2021, and they had events in Massachusetts where a lot of people got infected, and 90% of the viruses were the Delta virus, telling us that the Delta virus probably was vaccine resistant already in this case. And you can see the values here, the CT values, 21.54 for the unvaccinated and 22.77 for the vaccinated. And that is not a major change. It could be slightly higher for the vaccinated actually, but you cannot really have a significant difference. But it tells you it has no effect on how contagious you are if you are infected. This is my conclusion. And the solidarity argument is the opposite. The more people that get vaccinated, the higher risk for the people who need vaccines. Now we come to the third argument, reduces the risk of severe illness and death. One problem is the statistics from the officials is full of bias that will favor the outcome of the vaccine. And one thing that Sven talked about is the definitions, how you define unvaccinated and vaccinated. And it strongly benefits the vaccine effect. Also, they are ignoring to report the outcomes directly after vaccination. They put it on the unvaccinated group, and it actually is an increased risk of being infected both by coronavirus and other virus if you are vaccinated. Maybe 7-10 days afterwards you have a higher risk of getting infected, and that is because the immune system prioritizes the most severe threat. So if you put the vaccine in the arm, the immune system will go there and take care of that, while maybe if you have a natural infection in your mucus, it will be left alone for some time until the vaccine is under control. So that means that you can get higher levels of virus in the mucus. And that means later on, when the immune system is activated, you will have more severe symptoms. This is an example of Israel. My husband, who is a mathematician, he saw suddenly the death rates in COVID-19 in Israel started to increase very, very high levels. And he said, what is going on? And he found out that there was a sort of a campaign, vaccinated people over 60 years with a third dose. And this actually, if you look here, this is an example of on the hospital, very severe, in the same period, very severe sick people in hospitals with COVID-19. The highest death rates you find in the you find in the people who have received the third dose, and you can see there's a few days here after the campaign. Gör jag fel? Do I do this? It's quite an enormous change, sorry. The same you could also see in Vietnam, a lot of people dying from after vaccine campaigns. This is a small country, that's why you can see this kind of effects. Now we talk about reduced cost of medical care and sick leave. Of course, I think this is very important for many politicians. They want to, in Sweden, you also get sick leave for children, which they want to reduce because parents with small children stay at home a lot to take care of sick children. They also want lower hospital occupancy. And this is from 2009 when I looked at the report that was going to promote mass vaccination against the swine flu. And what you can see, the biggest cost here that they're going to save by mass vaccination is sick leave from child and sick leave self. Also, deceased people will increase enormously by mass vaccination. But sick leave tends to be a very important argument. And here is also exaggerated numbers. They claim that if we not start the mass vaccination, 1.2 million people will die from the swine flu. No, not die. They will need hospitalization, which was huge överdrift. Exaggeration. Thank you. So I think this is arguments that have been sold in to the politicians to support this. Improves public health. What I think is the most severe is that you don't get the broad T-cell memory against inner proteins. And if you do that for a long time, you will be quite in a bad situation. Actually, I saw data during 2009 from America and Canada, where they had the highest death rates in the swine flu. And a Canadian study showed that people who have had injections against flu yearly had a double as high death risk as people who didn't, which I think is it didn't protect them. Actually, you lose your the T-cell memory. So another thing that worries me, I don't know if it's true, is tendencies of showing tolerance development. You know, you treat children with higher and higher dose of the antigen to make them be tolerant to their antigen and don't react so strongly. Here, there's also, in people who had many dosage, there are some signs that this might downregulate your immune system. You get tolerant. And what happens if we are not reacting with the immune system against virus infection of corona type? It's not good, I think. I don't know if this is true, but it's a factor that worries me. And also the innate immune system might be affected. And what I think is very important is the herd immunity synchronization, because when it ends for everyone. So if it comes a new virus, you have no immunity in the population. It could be very bad. It could spread like fire, and that could be very, very dangerous. Normally, we have a variation in immunity in different individuals, but here you have, if you synchronize it with yearly immunization against all kinds of things, especially viruses that comes every year, could be dangerous when the vaccine doesn't work. Oj, sorry, jag ska trycka där. So is mass vaccination an optimal strategy to limit spreading or not? I don't think so, because I think there's a selection of vaccine-resistant virus variants. So you actually cause more problems than you are solving. And individuals who are dependent on vaccine will lose their vaccine protection faster. And you get a more narrow immunity because it's focusing on a small protein only. And you synchronize a lot of people in large populations. So, and it also inhibits the development of what I think one of the most important protection against this kind of respiratory virus, the broad T-cell memory, long time protection against severe infections. So, and I think that children are the ones that we should protect from this mass vaccination with different kinds of flu and coronaviruses and so on, because before puberty they are building up their immune system, and if they don't build it up correctly, what will happen when they are grown up? Maybe they have the first infection, flu infection when they are older. They can get very, very, very sick. Yes, that's what's me. And I would just say thank you for this pressure, and thank the organizers for a very nice conference. Hopefully I didn't talk too much.
Thank you very much.